Okay, welcome back to the discussion paper of CIE for A level, and the topic is the stress strain and the Young modulus. Now we are going to state the Hooke's law. What is the Hooke's law? The Hooke's law is when the extension, we know the extension is proportional to force or to applied force, or in other words you can say that force is equal to K times or in other words, from the definition we can say that the extension, which is delta L, is equal to force, proportional to applied force. So this is proportional symbol. It's like this. Okay, for part B, the variations of the applied force with the extension for a sample of material is shown in figure 3.1. Okay, so this is the figure. The sample behaved elastically up to an extension of 80 millimeter until 80 millimeter is proportional. Where is 80? Here, yeah? If we larger it, so 80. This is the limit of, what is it just now? The limit of proportionality. Extension of 80, still elastic, and break at point X. This one is point X. This one is point X. So this one, when it break, this one is elastic point. Then draw a cross to show the limit of proportionality. Label the cross with the letter P. Draw a cross to show the limit of proportionality. Label the cross with the letter P. So the limit of proportionality is when the graph is straight line. So how do we know that? Have to see it's straight line until about here, yeah, straight. So 40 to 80 is 20. 20 divided by 10 is 2. So 1 square is 2. So 42, 44, 46, 48, 60. How about 60? 60 here. So 60 going up. 60 going up. Yeah, it's about like this, yeah. The limit of proportionality is here. And then we have the y-axis is at this one. Wait, the y-axis, I think it's about here. Yeah, so this one is 5 point, because 4 to 6 is 2, and then 1 square is 2 divided by 10 is 0.2. So this one is 6, 5.8, so 5.6. It's 5.6. Yeah. So that, and it's 5.6, 60. So this is the cross. Just note it with the letter X. Okay, next one. Draw a cross to show the elastic limit. Label this cross with the letter E. Elastic limit is a point where the object still elastic. Yeah. The last point after the last point before it breaks. The last point before it breaks. So the label is crossed with the letter E. This that just now is P. E, where is E? Okay, so we have to see here that here at P. This one, yeah, it's already noted with elastic point. So this is called E. Okay, because this question say that elastically up to 80. So elastic limit is at the vinyl is at 80. This one, yeah? At 80. 80, and then this. It's like, yeah, 5.8 something. 5.8. The next one, the sample B has a cross-sectional area of 0.4 and initial length of 3.2. For deformation within the limit of proportional of the sample, determine the spring constants of the sample. The spring constant between the graph is force and extension. So we have the K is equal to force divided by extension, okay, or the area under, oh sorry, not the area under the graph, but if we divided the f divided delta x, we just find it the gradient. We'll find the gradient. Okay, so what is the gradient? The gradient is force divided by delta x. This is 5.6 divided by 60, yeah, 4.x. So 4.6, which is y over x. The gradient is y over x, which is 5.6 divided by delta x. 60 millimeter. So it's 60 millimeter minus 3 is equal to, if we divide them, 5.6 divided by 60 minus 3, so the answer is 93.3 Newton per meter. The next one, the Young modulus of the material from which the sample is made. So what is Young modulus formula? Young modulus formula is force per A times L divided by delta L, or X divided by delta X is also okay. So the force is, what is the force at here? Is, let's say the force is this one, 5.6, yeah, Newton. If the force is 5.6, means that the extension is 60. Just remember that 5.6 Newton times L, yeah, times L, the length is 3.2 divided by A, which is 0.4 millimeter square. To meter square is 10 to the power of minus 6 times delta L, which is just now 60 millimeter. Millimeter is minus 3. So based on the calculator, we'll get 5.6 times 2 is 11.2 divided by 0.4, 10 to the power of minus 6 times 60, 10 to the power of minus 3, which is 2.4 times 10 to the power of minus 8. We're using the calculator. 2.4 minus 8, so 4.6 4.67 times 10 to the power of 8 Pascal. So this is the answer for the Young modulus. Is there something wrong here? Wait, we will check it. 60 times 10 to the power of minus 3 is already correct. It's 5.6 times 3.2. Okay, I think it's correct. Yeah. The next one. Determine an estimate of the work done on the sample as it extended from zero extension to its breaking point. Explain your reasoning. The work done. So the work done is the area under the graph. Why they say there is no exact value for the work done at like this graph? We will find the work done from initial position to its breaking point. Okay, let we calculate it using the green one. To calculate the area in like this, we have to divide it into some form. Okay, so the first form is the triangle. This triangle. Okay, this triangle is the first, and then the second, like here. Let's say from here to from here. This one. Okay, this is the second one, which is number 2, and number 3 is not here. The green one. This is number 2. Wait, not there. Going there. Oh, and then down. Go there. This one is number 2, and number 3 is this. Number 3 is this. This one. Let's say this one is triangle. Sorry, rectangle. The number 3 and number 4 letter this one. Number 4, like triangle, yeah. Number 4. Okay, so we calculate number 1. Number 1, the area is triangle, yeah. Triangle half times base, which is 60 millimeter. Don't forget. Times height, which is 5.6. So we get from the calculator. So from calculator, 60 divided by 60 times 10 to the power minus 3 times 5.6 divided by 2. 0.168 joules, because it was one energy. For form number 2, the area is the length times the width, right? The length is from 200 to 60. 200 minus 60, which is this length, times the width, which is let's say this one. This one is 5.4, and the result is 140 times 5.4, which is equal to this one is still millimeter, yeah. So we have to divide by 1,000 later, times 1.4 divided by 1,000, which is 0.759. 6, yeah, joules. For number 3, we got this also, the length is the same, which is 200 minus 60, which is 140 times this. These are 3 square, which is 0 0.2, 0 0.4 and 0 0.6 Newton. This one is still millimeter, so we times it. 140 times 0 0.6 divided by 1000. 0.084. And the form for 4, we have triangle again, which is half times base. The base is, let's say, from here to there, yeah? So here it is in the middle between. So let's say 140 or 144. 144 minus 200 minus 144, which is the base, times height, which is 0 0.6, because there are only 3 square there. So this is equal to 200 minus 1 4 times 0 0.6 divided by 1000 is 0.0336 joules. So the total, so the work done is the area 1 plus area 2 plus area 3 area 4. If we are adding them together, 1.068 plus 1.0.756 plus 0.084 plus 0.0336. So the result is, the work done is 1.0416 joules. Okay, that's how to find the work done. The second sample wire of the same material has larger sectional area than original sample but the same initial length. The two samples are each deformed with a limit of proportionality. State and explain the qualitatively. Qualitatively means that without calculation, yeah? How the spring constant of the second sample compare with the original sample? How the spring constants of the second sample compares? So if the second sample wire, the second sample has larger diameter, okay, the larger cross-sectional area, larger A, okay, so it means that need more force to extend it. When it more force to extend it, it means that K, which is the constant, is proportionally to the force. The conclusion is that larger constant, larger spring constant, or the spring constant becomes the spring constant become larger because F is up, so K is also up because this one is proportional. Proportional means equal. So if the force is up, the K is also up. So the answer is the constant spring or the spring constant becomes larger. Okay. Or larger or greater, eh? think that's all. If you like, please subscribe. Thank you.